The 11th of November 2025, 4:23 a.m. Universal Time. While most of the Northern Hemisphere slept, a network of robotic telescopes across 3 continents turned their instruments toward the eastern horizon, searching for something that had been hidden from view for nearly 2 weeks. The target was 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system, and it had just emerged from behind the Sun. When the first images arrived at the Virtual Telescope Project facility in Manciano, Italy, astronomer Gianluca Masi leaned closer to his monitor. The comet was there, exactly where orbital mechanics predicted it would be, a fuzzy patch of light 14 degrees above the horizon. But something was different. Something had changed during those silent days when no human eye could follow its journey. An ion tail stretched across the field of view, glowing with the characteristic blue-green signature of ionized gas molecules being stripped away by solar wind. The Jufa tail extended at least 0.7 degrees across the sky, pointing toward the northeast, away from the Sun. And there, in the opposite direction, a fainter structure curved back toward the east-southeast, an anti-tail. A perspective effect caused by our viewing angle, where dust particles ejected weeks earlier now appeared to point in the wrong direction, creating an optical illusion that made the comet look like it was contradicting physics itself. This wasn't the same object that had disappeared behind the Sun in late October. The transformation was undeniable. Let's step back for a moment and understand what happened during those hidden days. On the 30th of October 2025, at approximately 14:47 UTC, 3I Atlas reached perihelion, its closest approach to our star. The distance was 1.4 astronomical units, roughly 130 million miles, just inside the orbit of Mars. For an object that had spent billions of years drifting through the frozen darkness of interstellar space, this was a baptism by fire. The Sun's radiation at that distance delivers approximately 520 watts per square meter. That's enough energy to sublimate water ice, to turn solid carbon dioxide directly into gas, to crack apart complex organic molecules that had remained stable for eons. The comet's nucleus, that solid core of ancient ice and dust no more than a few kilometers across, began releasing material at an accelerating rate. Gas molecules escaped from the surface, carrying dust particles with them, creating the glowing atmosphere we call a coma. But during perihelion, we couldn't watch. The comet's position relative to Earth placed it almost directly behind the Sun from our perspective, too close to the solar glare for ground-based telescopes to observe safely. Space-based instruments designed to study the Sun's corona, like NASA's SOHO spacecraft and the recently launched Punch mission, maintained their vigil. They captured the comet as a moving dot against the structured chaos of the solar wind, but their images lacked the resolution needed to reveal fine details. For those 2 weeks, 3I Atlas was alone with our star, undergoing transformations we could only imagine. The ion tail that now stretches across November's pre-dawn sky tells the story of that encounter. When solar ultraviolet radiation strikes gas molecules in the comet's coma, it strips away electrons, creating ions, electrically charged atoms and molecules. These ions respond to the Sun's magnetic field, which is carried outward by the solar wind at speeds exceeding 400 kilometers per second. The magnetic field lines grab the ions and pull them away from the comet, stretching them into a narrow tail that always points directly away from the Sun, regardless of the comet's direction of motion. This process happens to every comet that ventures close enough to a star. It's physics, predictable and understood. But what makes 3I Atlas remarkable is that this tail, so clearly visible now, was either absent or impossibly faint before perihelion. Amateur astronomers and professional observatories had been tracking the comet since its discovery on the 1st of July 2025. Throughout July, August, and September, as it crossed the orbits of Earth and Mars on its inbound journey, telescopes captured images showing a diffuse coma, a fuzzy envelope of gas and dust surrounding the nucleus. Some images showed hints of structure, subtle elongations that might have been the beginnings of a tail, but nothing like what we're seeing now. The Hubble Space Telescope observed 3I Atlas on the 21st of July 2025, when the comet was 277 million miles from Earth. Those images showed a teardrop-shaped cocoon of dust, redder in color than typical solar system comets, indicative of organic compounds being released from the surface. The dust created a coma, yes, but the ion tail was either too faint to detect or genuinely absent. NASA's James Webb Space Telescope turned its infrared instruments toward the comet in early August, capturing spectroscopic data that revealed the chemical composition of the gases being released: carbon dioxide, water vapor, carbon monoxide, carbonyl sulfide, the fingerprints of volatiles, ices that turn directly from solid to gas when heated. The data confirmed that 3I Atlas was actively sublimating, losing mass, transforming, yet still no prominent ion tail appeared in visible light observations. Then came perihelion. The intensity of solar radiation increased by a factor of 3 compared to the comet's position in early October. The rate of sublimation accelerated. More gas molecules poured into space, more ions formed, and when the comet emerged from behind the Sun on November 11, the ion tail was suddenly, unmistakably there. This raises questions that don't have simple answers. Was the tail always present, just too faint for our instruments to detect until the comet's activity level increased dramatically? Or did something fundamental change in the comet's structure or composition during perihelion, unlocking a reservoir of volatile material that hadn't been accessible before? Avi Loeb, the Harvard astrophysicist known for entertaining unconventional hypotheses about interstellar objects, published observations on November 5 showing images of 3I Atlas that appeared to lack a clear cometary tail. He noted that despite calculations suggesting the comet had lost more than 13% of its mass during perihelion, the expected dust tail wasn't visible. He questioned whether this anomaly might indicate something other than a natural comet. 6 days later, the ion tail appeared in multiple independent observations. Does this resolve Loeb's concern, or does it deepen the mystery? An ion tail and a dust tail are different phenomena. The ion tail is made of charged gas molecules pushed by magnetic fields. The dust tail is made of solid particles pushed by solar radiation pressure. They can exist independently. A comet might have one without the other, depending on its solar composition and activity level. What we're witnessing now suggests that 3I Atlas is rich in volatile ices that produce gas, but perhaps deficient in the fine dust particles that would create a prominent dust tail. That would be consistent with a comet that formed in the outer regions of another star system, where temperatures were so low that volatiles condensed efficiently, but dust grain growth was limited. The anti-tail adds another layer of complexity. This feature, pointing back toward the Sun rather than away from it, isn't actually moving in that direction. It's an illusion created by our viewing geometry. Dust particles ejected from the comet weeks ago have spread out along the comet's orbital path. Some of those particles now lie between us and the comet, creating a line of scattered sunlight that appears to extend sunward. It's a perspective effect, like railroad tracks appearing to converge in the distance even though they remain parallel. Anti-tails are rare but not unprecedented. They require specific geometric conditions. The Earth must be near the plane of the comet's orbit, and the comet must have been active long enough for dust to spread along its path. The fact that we're seeing an anti-tail now means 3I Atlas has been releasing dust for weeks or months, even if that dust hasn't formed a prominent conventional tail. As dawn broke over Italy on November 11, Gianluca Masi compiled his images into a time sequence, watching the comet drift slowly against the background stars. The ion tail flickered subtly, responding to variations in the solar wind. The anti-tail remained steady, a geometric ghost pointing toward a sun that was about to rise and wash away the darkness. This is the moment we've been waiting for since July, the moment when 3I Atlas, transformed by its encounter with our star, reveals what it has become. The comet is moving away from the Sun now, heading back out into the cold. Each day it travels 1.4 million kilometers farther from the warmth that triggered its awakening. The ion tail will persist for weeks as long as enough gas continues to sublimate, but eventually, as the comet crosses back beyond Mars' orbit, the activity will decline, the tail will fade, the coma will shrink, and 3I Atlas will return to being a cold, dark nucleus racing toward the stars. But for now, in these precious weeks of November and early December, we have a window. A chance to study an object from another star system in an active state, releasing the chemistry of its birth into space where our instruments can analyze it. Every spectrum we capture, every image we record, adds another piece to the puzzle of where this visitor came from and what its home system was like billions of years ago when our own solar system hadn't even begun to form. The transformation is complete. The hidden encounter behind the sun has ended, and now, as 3I, Atlas glides through the constellation Virgo toward its final approach to Earth, we watch and wonder what other secrets it might reveal before it disappears forever into the night. The chemistry unfolding in the coma of 3I, Atlas, is a message written in molecules, and decoding that message requires understanding what happens when ancient ice meets starlight for perhaps the first time in billions of years. Carbon dioxide dominates the volatile inventory of this interstellar visitor, and that single fact tells us something profound about where it came from. In our own solar system's comets, water ice is typically the primary volatile. Comets from the Oort cloud or Kuiper belt release plumes of water vapor when they approach the sun, creating the spectacular hydrogen clouds that extend for millions of kilometers. But 3I, Atlas, is different. The spectroscopic observations from NASA's James Webb Space Telescope in early August revealed carbon dioxide as the dominant outgassing species, with water present but secondary. This chemical signature points toward formation in an extremely cold environment, colder than the outer reaches of our own solar system. Carbon dioxide freezes at much lower temperatures than water under the pressure conditions found in protoplanetary disks. For CO2 ice to dominate over water ice in a comet's composition, that comet must have formed in a region where temperatures dropped low enough for carbon dioxide to condense efficiently, while water remained relatively depleted or was incorporated into other compounds. The star system where 3I, Atlas, originated was likely colder, dimmer, or more extended than our own sun's domain. Perhaps it formed around a red dwarf star, those small, cool stars that make up 70% of the galaxy, but whose habitable zones lie so close that they bathe their planets in stellar flares. Or perhaps it condensed in the outer disk of a sun-like star, beyond an equivalent of our Kuiper belt, in regions so distant that sunlight was little more than a bright point among countless others. The Webb telescope's near-infrared spectrograph didn't just detect carbon dioxide. The data showed water ice, carbon monoxide, and carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur atoms bonded together. This diversity of species suggests complex chemistry occurred in the comet's parent disk. Ultraviolet radiation from the young star, cosmic rays penetrating the disk, and possibly shock waves from the star's formation process all could have driven reactions that created these molecules and locked them into the ice. When solar radiation strikes the nucleus of 3I, Atlas now, in November 2025, it's not just heating the surface. Photons carry energy that breaks chemical bonds. Ultraviolet light with wavelengths shorter than 300 nanometers can dissociate water molecules into hydrogen and hydroxyl radicals. It can break apart carbon dioxide into carbon monoxide and atomic oxygen. It can shatter complex organics into simpler fragments. This process, called photodissociation, transforms the original ice composition into a secondary chemistry that fills the coma with reactive species. Those reactive species then interact with each other and with the solar wind. Hydroxyl radicals combine to form water again, or react with carbon compounds to create formaldehyde and methanol. Carbon monoxide can be ionized, stripped of an electron, becoming CO+, which responds to magnetic fields. The coma becomes a chemical laboratory where billions of reactions occur every second, driven by the relentless input of solar energy. And then there's the dust, or rather, the relative absence of it. Avi Loeb's November 5 observation highlighted an anomaly that mainstream astronomers had been discussing more quietly. Despite clear evidence of mass loss, despite the formation of an ion tail that we now see clearly, the expected dust tail remained elusive. For a comet losing 13% or more of its mass during perihelion passage, basic physics suggests that dust grains should be ejected along with the sublimating gas, pushed outward by the momentum transfer, and then swept into a broad, curved tail by solar radiation pressure. Dust tails are generally brighter and more visually spectacular than ion tails because dust particles scatter sunlight efficiently. They curve gently away from the sun, following the comet's orbital path, creating those sweeping arcs that make comets so memorable in photographs. But 3I, Atlas, at least in the images captured before mid-November, showed minimal dust tail structure. There are several possible explanations, and none of them require abandoning conventional comet physics. The first is particle size. Solar radiation pressure is most effective at pushing particles that are roughly the same size as the wavelength of visible light, around 0.5 micrometers in diameter. If the dust grains in 3I, Atlas, are significantly larger, perhaps tens or hundreds of micrometers across, they would be too heavy for radiation pressure to accelerate them into a prominent tail. They would simply fall back toward the nucleus or drift slowly along the orbital path, creating a diffuse, hard-to-detect cloud rather than a dramatic tail. The second explanation involves the dust-to-gas ratio. Comets from our solar system vary widely in how much dust they release relative to gas. Some are dusty, with ratios exceeding 1, meaning they eject more mass in solid particles than in gas. Others are relatively dust-poor, with ratios below 0.1. If 3I, Atlas, has an extremely low dust-to-gas ratio, its activity would be dominated by volatile sublimation, producing a strong ion tail but little visible dust tail. This scenario makes sense if the comet formed in a region where dust grain growth was inhibited. In the outer reaches of a protoplanetary disk, where densities are low and temperatures approach interstellar values, dust particles may remain small and poorly aggregated. The larger planetesimals that would become comets might accrete primarily volatiles with only a minor dust component mixed in. When such an object approaches a star and begins sublimating, it releases mostly gas, with dust playing a secondary role. The third explanation is geometric. Dust tails are best seen when we view them from the side or from below, looking up at the broad surface that scatters sunlight. If our viewing angle relative to 3I, Atlas's orbital plane, is such that we're looking almost edge-on at the dust tail, it would appear much fainter and narrower than it actually is. The recent appearance of the antitail suggests we are indeed viewing the comet's orbital plane at a shallow angle, which supports this interpretation. Or perhaps all three factors contribute: large dust grains, low dust production, and unfavorable geometry combining to make the dust tail difficult to detect even though it exists. This is the explanation most comet scientists favor, and it requires no exotic physics, no unconventional hypotheses, just a recognition that interstellar comets might have different properties than the solar system comets we're familiar with. But Loeb's point, the one that generates headlines and social media speculation, is that we shouldn't simply assume the conventional explanation is correct without rigorously testing it. Science advances by considering alternatives, even unlikely ones, and gathering evidence to rule them in or out. His suggestion that 3I Atlas might not be a natural comet, that it could potentially be a technological artifact, strikes most astronomers as extraordinarily implausible. The chemistry detected by Webb, the behavior observed by multiple telescopes, the morphology of the coma and tail, all are consistent with a comet. Nothing in the data requires invoking artificial origin. Yet the question itself is worth asking, not because the answer is likely to be yes, but because the process of answering it forces us to be rigorous about our assumptions. What evidence would definitively prove 3I, Atlas, is a natural comet versus something else? The chemistry is compelling but not conclusive. After all, a technological object could in principle be coated with ice or designed to mimic cometary behavior. The orbit is hyperbolic and clearly interstellar in origin, but that tells us where it came from, not what it is. The scientific method doesn't work by declaring certainty and refusing to examine alternatives. It works by forming hypotheses, making predictions, gathering data, and updating beliefs based on evidence. The hypothesis that 3I, Atlas, is a natural comet makes specific predictions. It should brighten as it approaches the Sun following a predictable curve based on sublimation physics. It should show spectral features consistent with known cometary volatiles. It should produce a coma and tail with morphologies explainable by gas dynamics and radiation pressure. And so far, every one of those predictions has been confirmed. The alternative hypothesis that it's something technological makes no specific predictions because we don't know what technological artifacts from other civilizations would look like or how they would behave. It's an untestable hypothesis in the absence of some clear anomaly that cannot be explained naturally. The missing dust tail, intriguing though it may be, doesn't rise to that level. It's an anomaly that has multiple conventional explanations, any one of which might be correct. What November's observations have shown is that the ion tail, at least, behaves exactly as expected. It appeared after perihelion when solar heating increased the sublimation rate. It points away from the sun, driven by the solar wind's magnetic field. It flickers and varies in response to changes in solar wind conditions. It's doing precisely what a cometary ion tail should do. The anti-tail, too, fits conventional understanding. It appeared because we're viewing the orbital plane at a favorable angle, and because the comet has been releasing dust for long enough that particles have spread along the orbit. These are features predicted by established physics, observed in other comets, and fully consistent with 3I. Atlas being exactly what it appears to be, an ancient, icy visitor from another star system undergoing the same processes that affect every comet that ventures too close to a star. The chemistry will continue to unfold over the coming weeks. As the comet moves farther from the sun and the sublimation rate declines, we'll see which molecules persist longest and which fade first. The more volatile species, like carbon monoxide, will likely cease outgassing before the less volatile ones, like water. This sequence will provide additional clues about the temperature profile within the nucleus and the layered structure of the ice. Ground-based telescopes equipped with spectrographs will continue measuring the ratios of different isotopes in the molecules being released. The ratio of deuterium to hydrogen in water, the ratio of carbon 13 to carbon 12 inches carbon dioxide. These isotopic signatures carry information about where and when the comet's material formed. Different regions of the galaxy, different stellar environments, produce slightly different isotopic compositions. By comparing 3I Atlas to solar system comets and to models of interstellar chemistry, researchers will narrow down the possible origins. The comet is talking to us in the language of chemistry, telling a story that began billions of years ago in a star system we'll never see. And as it continues outward, crossing the orbit of Earth one final time in December before beginning its long journey back to interstellar space, we're listening as carefully as we can, trying to understand what this ancient traveler is saying about the galaxy we share and the processes that shape worlds in the darkness between stars. The trajectory of 3I Atlas carries information encoded in pure mathematics, and when you trace that path backward through time, it points toward origins that challenge our assumptions about how long objects can survive in the hostile environment of interstellar space. The comet entered our solar system from the direction of Sagittarius, that constellation which marks the location of our galaxy's central bulge when viewed from Earth. This is significant because the previous two confirmed interstellar visitors came from different directions. 1I Oumuamua, discovered in October 2017, approached from the direction of the constellation Lyra, roughly toward the solar apex, the direction our sun is moving relative to the local standard of rest. 2I Borisov, discovered in August 2019, came from a direction in Cassiopeia, also in the northern celestial hemisphere. But 3I Atlas arrived from the south, from a direction opposite to the sun's motion through the galaxy. This suggests it wasn't simply overtaken by our solar system as we plow through the interstellar medium. Instead, it was moving on a path that intersected ours, approaching from behind relative to our galactic orbit. The geometry implies this object has been traveling through the Milky Way on a trajectory that originated somewhere in the dense stellar populations toward the galactic center, or at least from that general direction. The galactic center region is a fundamentally different environment than the solar neighborhood we inhabit. Star formation there occurs at higher rates, stellar densities are orders of magnitude greater, and the radiation environment is harsher, due to proximity to the supermassive black hole Sagittarius A times and the clusters of massive stars surrounding it. If 3I Atlas formed in a system near the galactic core, it would have condensed in conditions unlike those that produced our own solar system's comets. But there's a timing problem that makes this origin story complicated. The age estimates for 3I Atlas range from 3 billion to 11 billion years. Our solar system is 4.6 billion years old. If this comet is 11 billion years old, it formed when the universe itself was only 2.7 billion years old, in the epoch when the first substantial generation of sun-like stars was just beginning to produce planetary systems. It would predate not just our solar system but the majority of terrestrial planets in the galaxy. An object surviving for 11 billion years in interstellar space faces relentless erosion. Cosmic rays, high-energy particles accelerating through the galaxy, strike the surface continuously, breaking chemical bonds and altering the ice composition. Starlight from the billions of stars the object passes at varying distances heats the surface, driving gradual sublimation even in the coldness of space. Collisions with interstellar dust grains, rare but inevitable over billions of years, sandblast the surface, removing material layer by layer. Theoretical models of interstellar comet survival suggest that objects smaller than a few kilometers across would be substantially eroded over timescales of billions of years. The fact that 3I Atlas still possesses abundant volatiles, enough to create the activity we're observing now, implies either that it's toward the younger end of the age estimate range, or that it's larger than current observations suggest, with a thick, insulating crust that protected the interior volatiles from cosmic weathering. The Hubble Space Telescope's observations in July provided an upper limit on the nucleus diameter of approximately 5.6 kilometers, though it could be as small as 440 meters. That's a wide range of uncertainty, reflecting the difficulty of distinguishing the solid nucleus from the surrounding coma, even in high-resolution images. If the nucleus is on the larger end of that range, several kilometers across, then it would have enough mass to retain volatiles over billions of years through sheer volume, with the surface layers sacrificed to erosion while the interior remained pristine. The speed provides another clue. When 3I Atlas entered the solar system from interstellar space, it was moving at 58 kilometers per second relative to the Sun. That's its hyperbolic excess velocity, the speed it would have far from any gravitational influence. It's faster than Oumuamua's 26 kilometers per second and Borisov's 32 kilometers per second. It's moving fast enough that it will cross the solar system in less than a year from discovery to departure, and fast enough that no planet's gravity could have accelerated it to that speed starting from solar system origins. This speed tells us something about the object's journey through the galaxy. Objects bound to the Milky Way's gravitational potential move at velocities determined by their orbital characteristics around the galactic center. Stars in the solar neighborhood, including our Sun, orbit at roughly 220 kilometers per second. The random velocities relative to that average, the so-called peculiar velocities, are typically 20 to 40 kilometers per second. An object with a 58 kilometers per second velocity relative to the Sun could easily fit within this distribution, suggesting 3I Atlas is simply a comet that was ejected from its parent system, perhaps billions of years ago, and has been orbiting the galaxy ever since, following its own path through the spiral arms until chance brought it near enough to our Sun for gravity to bend its trajectory inward. But there's another possibility, one that's more speculative but worth considering. If 3I Atlas is indeed 11 billion years old and originated near the galactic center, its velocity might reflect the different orbital dynamics of that region. Stars closer to the galactic core orbit faster, and objects ejected from systems there might carry higher velocities. Alternatively, if the comet was ejected during a close encounter between its parent star and another star, a process that can impart substantial velocity kicks, it might have been traveling at high speed relative to the local stellar population for billions of years. The trajectory also reveals what will happen next. After passing behind the Sun in late October and emerging into the predawn sky in November, 3I Atlas is now on an outbound path. It crossed Mars's orbit on November 3, It will make its closest approach to Earth on the 19th of December 2025, passing at a distance of approximately 1.8 astronomical units, about 170 million miles. That's farther than the Sun, so there's no danger of collision or even particularly close encounter. But it's close enough for ground-based telescopes to obtain detailed observations, close enough for Hubble and Webb to point their instruments toward this visitor one last time before it recedes beyond their reach. After the Earth flyby, the comet will continue outward, crossing the orbit of Jupiter in March 2026. It will pass through the asteroid belt, through the realm of the gas giants, and, eventually beyond the Kuiper belt, returning to the interstellar medium from which it came. The Sun's gravity will slow it down as it climbs outward, but never enough to capture it. The trajectory's eccentricity, that parameter describing the shape of the orbit, is 6.137. Anything above 1 is hyperbolic, unbound. An eccentricity above 6 means the path is almost a straight line, barely curved by the Sun's gravity. By the year 2030, 3I, Atlas, will be farther from the Sun than Neptune. By 2050, it will be beyond the heliopause, the boundary where the solar wind gives way to the interstellar medium. By 2100, it will be so distant that even our most powerful telescopes won't be able to detect it. And then it will travel for hundreds of thousands of years, possibly millions, before it passes near another star, before another civilization, if one exists, has the chance to see it gliding through their skies and wonder where it came from. The comparison to the previous interstellar visitors is instructive. Oumuamua was strange from the beginning. Its elongated shape, inferred from the way its brightness varied as it tumbled, suggested an object with an aspect ratio of at least 6:1, possibly 10:1. Nothing in our solar system looks like that. Its non-gravitational acceleration, a tiny but measurable deviation from the path predicted by gravity alone, sparked intense debate. Was it outgassing like a comet, producing thrust from jetting volatiles? Or was it something else, perhaps a light sail pushed by solar radiation, as Avi Loeb proposed? We never saw a coma or tail around Oumuamua, despite extensive observations. If it was outgassing, the rate was so low that the gas remained undetectable. This led to the competing hypotheses. Either it was a comet with extremely low activity, possibly because it had already passed close to the Sun in the distant past and lost most of its volatiles, or it was not a comet at all, but rather an asteroid or something more exotic. 2I, Borisov, discovered 2 years later, was unambiguously a comet. It showed a clear coma and tail from the moment of discovery. Spectroscopic observations revealed water vapor, carbon monoxide, and cyanide, all typical cometary volatiles. Its behavior was so normal, so similar to solar system comets, that it almost seemed disappointing. Here was an interstellar visitor that looked and acted like something we already understood. The main scientific value was in measuring its composition and comparing it to solar system comets to see if there were subtle differences that might reveal something about its formation environment. And now 3I, Atlas, occupies a middle ground. It's clearly active, releasing gas and dust, producing tails that mark it unmistakably as a comet. But it has quirks: the CO2 dominance, the relative lack of a dust tail, the late appearance of the ion tail after perihelion. These quirks don't make it alien in the technological sense, but they do make it distinct, a reminder that interstellar comets might have properties distributed across a range that extends beyond what we've seen in our own comet population. 3 objects, 3 different characteristics, and from this sample of 3, we're trying to infer the properties of trillions of similar objects drifting unseen through the galaxy. It's like trying to understand Earth's biodiversity by examining 3 randomly selected insects. The sample is too small to draw firm conclusions, but it's enough to tell us that diversity exists, that interstellar space is not filled with identical objects, but rather with a population that varies in size, composition, structure, and behavior. The next decade will bring more discoveries. The Vera C. Rubin Observatory, currently completing commissioning in Chile, will begin its legacy survey of space and time in 2025, scanning the entire southern sky every few nights with a camera so powerful it can detect objects hundreds of times fainter than current surveys can find. Simulations predict Rubin will discover 1 or 2 interstellar objects per year, possibly more. Within 10 years, we might have a sample of 20 or 30, enough to begin understanding the population statistically. But 3I, Atlas, won't be among those future discoveries. It will be gone, racing outward at 58 kilometers per second, carrying its ancient chemistry back into the darkness. This is our moment. These few months between July 2025 and early 2026, to learn everything we can from this visitor. And as telescopes around the world and in space point toward Virgo, toward that moving point of light that has traveled farther and longer than anything else we've ever studied up close, we're reminded that the galaxy is vast, old, and full of wanderers whose stories intersect with ours for the briefest of moments before diverging again into separate futures. The 19th of December 2025. Mark that date. In 37 days from now, 3I, Atlas, will reach its closest point to Earth, passing at a distance of 170 million miles. That's farther than the Sun hangs above us, farther than Venus at its nearest approach, but closer than this comet will ever come to our planet again. After December 19, the distance will only increase. The angle will only widen, and eventually, probably within our lifetimes, this visitor will fade beyond detection, becoming one more invisible traveler in the sea of darkness between stars. This final flyby represents something more than just another observational opportunity. It's a moment of connection, a point where 2 objects with radically different histories briefly share the same region of space. Earth, a world that has harbored life for at least 3.5 billion years, orbiting a star that formed from the collapse of a molecular cloud 4.6 billion years ago. And 3I, Atlas, a frozen remnant, possibly 11 billion years old, born in a system that might have already died and scattered its atoms back into the interstellar medium long before our sun ignited. These 2 objects will never meet like this again. The geometry that brought them into proximity, the precise alignment of trajectories across the 3-dimensional space of the solar system, is a configuration that will not repeat. After 3I, Atlas, departs, it will travel through the galaxy for millions of years before encountering another star system. And by then, Earth will be in a different epoch entirely. The continents will have rearranged themselves, the climate will have cycled through ice ages and warm periods we cannot predict. The species inhabiting the surface, if any remain, might be unrecognizable descendants of the forms we know today. But in December 2025, we're here. We have telescopes, we have spectrographs and cameras, and the accumulated knowledge of centuries of astronomy. We can point our instruments at this visitor and ask questions that our ancestors could never have conceived. What is your chemistry? Where were you born? How long have you traveled? And though the comet cannot answer in words, it answers in photons, in spectra, in the reflected sunlight and emitted gas molecules that carry information encoded in wavelengths and velocities and abundances. The observations planned for December are ambitious. Hubble will image the comet again, tracking any changes in the coma's size and structure compared to the July observations. The goal is to measure whether the nucleus has fragmented, whether the activity level has increased or decreased, whether there are jets or localized sources of outgassing that might indicate active vents on the surface. These details constrain models of how the nucleus rotates, how heat penetrates into the subsurface layers, and how stable the structure is under the stress of solar heating. Webb will take additional spectra with multiple instruments, capturing infrared light, that reveals the warmest parts of the coma and the molecules that emit most strongly at those wavelengths. By comparing December spectra to the August data, astronomers can track how the composition changes as the comet moves farther from the Sun and cools. Do the relative abundances of different molecules shift? Does the isotopic composition remain constant, or do different ice layers with different isotopic signatures become exposed as the surface erodes? Ground-based observatories equipped with adaptive optics, systems that correct for atmospheric turbulence in real time, will attempt to resolve the nucleus itself, separating it from the coma and measuring its size directly rather than inferring it from brightness. This is extraordinarily difficult because the nucleus is small and faint, overwhelmed by the surrounding cloud of gas and dust. But if it can be done, It would provide the single most important physical parameter, the actual size of the solid body at the center of all this activity. Radio telescopes will search for emissions from complex molecules, the organic compounds that might exist in trace amounts but which carry disproportionate significance. The detection of formaldehyde, methanol, ethanol, or even more complex species like amino acids would suggest that the chemistry in the comet's parent disk was rich and active, capable of producing the building blocks of life. These molecules are fragile and easily destroyed, so their presence would indicate they were either continuously produced during the comet's formation or protected deep within the ice structure until now. And amateur astronomers will contribute as well. Thousands of telescopes around the world, operated by individuals who dedicate their nights to watching the sky, will image 3I, Atlas, and submit their data to international databases. This distributed network of observers provides continuous monitoring that no single professional facility can match. Comets can change unpredictably, undergoing sudden outbursts or fragmentations, and having eyes on the target around the clock increases the chance of catching such events. The December flyby is our last good look, but it's not the absolute end. The comet will remain detectable for months afterward, gradually fading as it recedes and its activity declines. By mid-2026, it will probably drop below the threshold of most telescopes, visible only to the largest observatories as a faint point of light with no discernible coma. And then, sometime in late 2026 or early 2027, it will fade completely, becoming too faint for even Hubble or Webb to track. At that point, 3I, Atlas, transitions from an observed object to a memory, a dataset, a collection of images and spectra archived in databases where future researchers will return to them, analyzing them with techniques we haven't invented yet, asking questions we haven't thought to ask. The comet will still exist, of course, still racing outward on its hyperbolic trajectory, but it will have passed beyond the reach of our instruments, beyond the light-gathering power of our largest mirrors. This is the nature of interstellar visitors. They arrive unannounced, pass through our neighborhood in months or years, and then depart forever. We don't get second chances. We don't get to send a probe to follow them, not with current technology. The fastest spacecraft we've ever built, the Parker Solar Probe using the Sun's gravity to accelerate, reaches speeds of 190 kilometers per second at perihelion, but that's in a highly elliptical solar orbit. To catch an interstellar object moving at 58 kilometers per second outbound from the Sun, we'd need a spacecraft that could not only match that velocity, but do so within the few months when the object is close enough for detection and trajectory calculation. ESA's Comet Interceptor mission, scheduled for launch in 2029, is designed as a first step toward this capability. The spacecraft will wait in orbit at the Earth-Sun L2 Lagrange point, positioned to respond quickly when a suitable target is discovered. The mission profile assumes a pristine comet from the Oort cloud, something on its first passage through the inner solar system, but the design could potentially be adapted for an interstellar object if one were discovered with sufficient lead time and a favorable trajectory. The mission concept is a pathfinder for what future generations might build. Rapid response probes that can launch on short notice, accelerate to high velocities using advanced propulsion, and intercept these visitors before they escape back into the void. Imagine a spacecraft reaching 3I, Atlas, not in December 2025 but in December 2024, arriving while the comet was still inbound, before perihelion. It could have flown alongside this ancient wanderer, measured its surface temperature, analyzed the composition of freshly ejected gas, captured images of the nucleus at resolutions high enough to see individual boulders and ice layers. We don't 10% have that capability yet. But the fact that we're seriously planning for it, designing missions and technologies that might make it possible within decades, represents a fundamental shift in how we think about our place in the galaxy. We're no longer passive observers of objects that happen to pass through. We're beginning to imagine ourselves as active participants, capable of reaching out to these visitors and studying them up close. But even without interception missions, even with just remote observations from Earth and its orbital telescopes, we're learning profound things. The 3 interstellar objects detected so far have taught us that such objects are relatively common. The discovery rate, roughly one per year now that our survey capabilities have improved, suggests there are billions of similar objects within a few light-years of the Sun at any given time. Most are too faint and too far to detect, but they're there, a vast unseen population of wanderers filling the space between stars. This realization changes the picture of the galaxy. We used to imagine interstellar space as essentially empty, a void between the islands of star systems. But it's not empty. It's populated with debris, with the cast-off remnants of planetary formation, with comets and asteroids and possibly larger bodies ejected from their parent systems by gravitational interactions with planets or other stars. Every star system likely produces millions or billions of such objects over its lifetime, and they accumulate in interstellar space, orbiting the galactic center on their own independent paths. These objects carry chemistry with them, ice and organics that formed in protoplanetary disks and were preserved in the deep freeze of space. When they occasionally fall into another star system, as 3I Atlas has fallen into ours, they deliver that chemistry. Over billions of years, over the countless passages of interstellar objects through every star system in the galaxy, this process might seed worlds with the ingredients for life, spreading complex molecules and perhaps even biological precursors across interstellar distances. This idea, called panspermia in its strongest form, remains speculative. We have no direct evidence that life can survive the journey through interstellar space or that it has ever been transferred between star systems. But the chemistry can certainly travel. The molecules detected in 3I Atlas, the carbon dioxide and water and organics, are the same molecules that might dissolve in the oceans of a young planet, contributing to the prebiotic chemistry that eventually leads to the first self-replicating systems. In this sense, 3I Atlas is not just a curiosity, not just a scientific target, but a courier. It's carrying a sample of the galaxy's chemistry through our solar system, offering us a glimpse of conditions elsewhere. And while it won't deliver its cargo to Earth, won't crash into our planet and deposit its molecules into our biosphere, it's doing so somewhere. Statistically, over the billions of years that interstellar objects have been drifting through the galaxy, some must have collided with planets, including planets with oceans and atmospheres capable of supporting life. The universe is speaking through these visitors. Each one is a word in a conversation that spans billions of years and encompasses the entire galaxy. Oumuamua was a word. Borisov was another. 3I Atlas is the latest, and there will be more. With each new detection, we're learning the vocabulary, beginning to understand the grammar of how star systems form and evolve and send their remnants out into the cosmos. And as we watch 3I Atlas drift through Virgo in these final weeks of November, approaching the moment of closest approach in December before receding forever, we're part of that conversation. We're observers and participants both, conscious beings on one small world, taking note of an ancient traveler from realms we'll never visit. The comet doesn't know we're watching. It doesn't care. It's following the laws of physics, responding to gravity and solar radiation, sublimating ice and releasing dust, because that's what comets do when they approach stars. But we know, we care. And in some distant future, when humanity has perhaps spread beyond Earth, when we have telescopes powerful enough to detect objects around other stars and spacecraft fast enough to visit them, we might find another comet, one that originated here, one that was ejected from our own solar system billions of years ago and has been traveling ever since. And when we do, we'll recognize it as kin, as something that shares our origins, and we'll understand that the galaxy is not a collection of isolated systems, but a connected whole, where matter and energy and information flow across vast distances, linking stars and worlds and perhaps even civilizations in patterns too large for any one species to fully comprehend. For now, we have December. We have one more month of observations, one more chance to point our instruments at this visitor and ask our questions. And then, like everyone who has ever looked up at the night sky and wondered about the lights moving against the fixed stars, we'll watch it go. We'll mark its passage in our records, in our papers and databases and collective memory. And we'll wait, with patience and with instruments ready, for the next visitor to arrive, carrying news from the galaxy, telling stories written in the language of chemistry and motion about worlds we've never seen and times almost too ancient to imagine. Sleep well, knowing that above you, threading through the darkness, ancient wanderers are passing. They've traveled farther than thought can easily follow, survived longer than civilizations endure, and they're still moving, still carrying their frozen cargo, still waiting for gravity to curve their paths toward the next encounter, the next star, the next chance for someone, somewhere, to look up and say, "There, that light that moves, where did it come from? And what can it tell us about the universe we share?" The ion tail of 3I, Atlas, stretches across the predawn sky, a faint blue-green line pointing away from the sun. The antitail curves subtly in the opposite direction. And somewhere between those two structures, invisible at the center of the glow, the ancient nucleus tumbles through space, slowly rotating, gradually warming as solar radiation penetrates its surface, releasing molecules that have been frozen since before Earth existed. This is the moment. This is the convergence. And in 37 days, on December 19, when the geometry aligns for the closest approach, we'll be watching. Not because we expect anything dramatic, not because the comet will put on a show, but because it's there, because it came from somewhere else. Because understanding where it came from and where it's going helps us understand where we are in the vast architecture of the cosmos. The universe is ancient, the galaxy is vast, and we are here, now, watching a visitor pass through, learning what we can in the brief window before it disappears forever into the night.